The first of Eli Grigsby's lectures. We'll hear from Boston College, who's going to tell us about annular Khovanov-Lee.
All right, can you hear me? You can.
Yeah, correct.
Can you guys hear me? Okay, good. Okay, so I'm going to be talking a little bit about Khovanov homology of links viewed as braid closures. Actually, Khovanov homology of links viewed as braid closures. I think that the main goal of these lectures was really to understand how the representation theory of SL2 was relevant to the topology of braid closures. Well, rather, the interaction between Khovanov homology and the representation theory of SL2 was relevant to the topology of braid closures. I realized that there isn't very much actually explicit that we know right now, but there are a lot of interesting connections between the applications that we currently have to topology and this SL2 representation theory. So what I'm going to try to do is at least highlight where SL2 representation theory makes an appearance in Khovanov homology. And I'll start by talking about a theorem that I proved with John Baldwin a couple of years ago. And it's, I think it's also a nice place to start because it's along the same kinds of lines that of things that Tony has been talking about detecting the trivial braid or faithful categorical representations of the braid group. So what I'm going to be talking about today is a way of detecting the trivial braid using Khovanov homology. And I should note before I start, so that's the main goal of my lecture today, but I should note before I start that there do exist better algorithms for detecting the trivial braid out there than the one I'm going to describe. But I think it's nice because it also connects a little bit. One of the main ingredients in the proof is a particular left invariant, or rather, actually, the way that I talk about it's a right invariant order on the braid group that people should know about as well. And so that connects a little bit with what Cameron was talking about. And the SL2 representation theory does not make an appearance until lecture 3. Sorry about that. I thought I'd make an appearance today. But at least the main players in that connection, or at least one of the main players in that connection, will make its appearance today. Okay, so with that long-winded introduction, let me just remind you, where's all the chalk? Okay, so I'm going to be talking about the braid group. So notation, when I say BN, I'll mean the n-strand braid group. And of course, by an n-strand braid, we typically think of an n-n tangle. So most of my braids will be called sigma. And it's an n-n tangle in the thickened disk where we have n sort of fixed, chosen endpoints at the bottom, and n fixed points typically chosen to lie on, if you think of the disk as being the unit disk in the complex plane, these points are typically chosen to lie on the R axis so that they're ordered from left to right. And so here's an example of a 3-strand braid. The point is that the restriction of the obvious Morse function to this tangle has no critical points. And we're considering such objects rel boundary through such such objects, through isotopy through such objects. Okay, so why do low-dimensional topologists like braids? Well, because they like links, and you can take the closure of any braid to get a link. So here is a somewhat uninteresting link. And I'll denote the closure of a braid by sigma hat. And this is, I mean, when low-dimensional topologists talk about taking closures of braids, typically they're talking about viewing it up to isotopy in S3. But I'd like to point out that as sort of an intermediary three-manifold that this braid closure sits in, of course, really the braid is in the complement of its axis. So that's the thing that goes all the way around here, which we can think of as being like the z-axis in S3 union the point at infinity. Or sorry, the z-axis in R3 union this extra point at infinity. And this is really D cross S1. It's a solid torus. Okay, so so that's what I mean by a braid and its closure, a geometric braid and its closure.
Can I ask a naive question?
Yeah.
So it seems that you've defined braids as like certain kinds of tangles, not a certain kind of equivalence. So in particular, it seems like they shouldn't be the same as that kind of tangle, right? Like there should be two braids which are equivalent as tangles, but not as braids. Because it seemed like you wanted to like pass through an isotopy of braids then.
Yeah, I think it is, but
Great.
but we consider isotopies through braids because it's convenient. Okay, so of course the sort of starting theorems in this subject are the Alexander theorem, which of course says that every link in S3 can be realized as a braid closure, can be realized as some braid closure for some index n. So every link can be braided about an axis via an isotopy of links. And then the Markov theorem. Which says that if two braid closures are isotopic as links, then they're related by a finite sequence of so-called braid isotopies, conjugations, and stabilizations and destabilizations. So they're related by a finite sequence of braid isotopies conjugations. So remember, this is a group. So these conjugations are actually conjugations in the group. And Markov stabilizations and destabilizations. And I just want to point out here, there's sort of a, well, not just sort of, but there is sort of a partitioning of the kinds of isotopies in S3 we're considering. So these braid isotopies are really isotopies rel boundary in the disk cross I. So these are, and they're braid-like. So these are just R2 and R3 moves in the disk cross I. So these are relative isotopies in the disk cross I. So these are relative isotopies of the original braid. And again, these are just R2 and R3 moves because we're just focusing on braid isotopies. And then if you look at the first two, these are isotopies in this disk cross S1, this solid torus. And again, just R2 and R3 moves. So these are R2 and R3 moves. And these Markov stabilizations and destabilizations are R1 moves that, to keep things braided, need to pass through the z-axis. So these are R1 moves. So this is plus. So I guess I should say everything that came before plus, plus a little more, and then these three are everything that came before plus these R1 moves. Passing across the braid axis. Okay, so so this is the setup, and of course what we're trying to do somehow is detect the trivial braid. The trivial braid being the one where nothing happens. Okay. And we'd like to use Khovanov homology to do this. So before I give you something of a crash course in Khovanov homology, let me just tell you, roughly speaking, what we're going to do. So Khovanov homology is a theory due to Khovanov from the late 90s that associates to a link, or rather the diagram of a link, diagram of a link in S3. Well, from this, combinatorially, you write down a chain complex. Let's call it, actually, I think, so this is a chain complex. And by the way, for today's talk, so all my chain complexes are going to be over fields, and for today's talk, my field will be Z mod 2. It will change for the second two talks. So a chain complex over F. And now if you take the homology of this chain complex, you get an invariant of the link. So by the way, also all my links will be oriented. Okay, so now we're concentrating on links viewed as braid closures. And what Plamenevskaya noticed is that now if L, well, I guess really if the diagram of L, so if you have the diagram of L is actually the diagram of a braid closure, then you can extract, there's a canonical class. Right, so there's some braid. Then there's a distinguished generator, or a distinguished basis element in this chain complex, which I'm going to call V minus of this braid closure. And I'll also drop the diagram from the notation so I don't have to write so much. So there's a distinguished generator of the chain complex. And it happens to be a cycle. So in particular, it represents a homology class in Khovanov homology. So this is her notation for, and will be our notation for an invariant that she defines, which is just the homology class of this distinguished cycle. And you may ask, an invariant of what? It actually turns out not to be a link invariant. It turns out to be an invariant of the transverse isotopy class. Of this braid closure. I won't say much about transverse isotopy today. I will say a little bit next time. So with respect to the standard tight context structure in S3. Which I think Andy talked a little bit about in his mini course. But from our point of view today, all we care about is that it's also an invariant of the conjugacy class of sigma hat. So hence an invariant of the conjugacy class. And that's what we're going to use for this trivial braid detection. Because of course, if a braid is conjugate to the trivial braid, then it is the trivial braid. Invariant of conjugacy class of sigma. Okay. So it's this invariant that we're going to use to detect the trivial braid, and hence solve the word problem in the braid group. So what do I mean by that? If you have, typically you have braids written as words in these elementary Artin generators, these half twists between adjacent strands, and you might see some such word and wonder whether it represents the trivial element of the group. Or you might take two such words and wonder whether they're actually representing the same element. That's the word problem. And if you want to see whether because you're working in a group, if you want to see whether two words represent the same element, all you have to do is just multiply one by the conjugate of the other and see whether it's the trivial braid. Okay, so here's the theorem. So let's let sigma be an n-strand braid. Then sigma is the trivial braid if and only if, when you compute the Plamenevskaya invariant, so this is some homology class in Khovanov homology. If it's non-zero and the Plamenevskaya invariant of the mirror of sigma is also non-zero. So remember what I mean by the mirror is just take some braid closure diagram and change all the crossings. Or put differently, in the word, the word in the Artin generators, change all the pluses to minuses and minuses to plus in the exponents. Okay. Okay, any questions so far about the basic setup? I haven't told you anything about Khovanov homology or Plamenevskaya's invariant, really. But at least ask me questions if you don't see what I'm trying to do here. Okay, so we're going to try to understand the proof of this theorem. Okay. Actually, before I go on, I should say that that the idea of doing this arose from a conversation that I had with Matt Hedden and Jeremy Van Horn Morris. So they had noticed that something. This is completely an aside if you like Heegard-Floer homology. But there's a contact invariant in Heegard-Floer homology, which Andy talked about in his class. And Plamenevskaya's invariant is really morally analogous to that contact invariant. It has many structural similarities. And so a similar theorem is true for the contact invariant in Heegard-Floer homology. Namely that if you look at a contact invariant, then it's supported by some open book, and it turns out that that the contact invariant is non-vanishing for that open book and for the open book of the mirrored monodromy, if and only if that monodromy is trivial. And this appears, I think, in a paper of Matt with Liam, with botany in the title. Okay. Okay. So let's talk about Khovanov homology of braid closures. So this is something of a crash course in Khovanov homology. I'll tell you kind of the bare minimum that you'll need to know to understand the Khovanov homology of braid closures. And today, because a lot of what makes this theory interesting is actually the gradings in the theory, but on the flip side, when a speaker starts talking about gradings, everybody just falls asleep immediately. I'm going to introduce the gradings slowly. Today, all we need to know about is one of the gradings, and we'll talk about the other ones later. Okay, so this is the Khovanov homology of braid closures. Okay, so let's start with a diagram, which is realized as a diagram of a braid closure. Actually, I wanted to do something a little bit different. So this is really a two-crossing diagram of the two-component unlink realized as a braid closure. Okay, so the idea is that if you have at every crossing, there are two ways to resolve the crossing, a so-called zero resolution and the one resolution. And so now if you order the crossings, which if you have so again, braids naturally come with an orientation. So say we're reading from bottom to top, then let's orient our braids in that way. So the crossings are also ordered if this braid is represented by a word. Okay, so now from this data of the diagram and an ordering of the crossings, you can construct what's called a cube of resolutions. So if there are C crossings, then you look at the binary strings of length C, and each one of those binary strings of length C specifies for you a complete resolution. So changing each of the crossings to one of the two resolutions as specified. So in this case, or this is 0, 0. This is 1, 0, 0, 1, 1, 1. Hopefully I did that right. Okay, and now notice that so each of our vertices in this cube of resolutions corresponds to a complete resolution. Each of our edges corresponds to an elementary saddle cobordism where you've just changed the resolution at a single crossing. Okay, so now you hit this whole picture with some sort of 1 + 1 dimensional TQFT. So you're now going to assign to each vertex of this cube of resolutions a vector space, and to each edge a linear map between vector spaces. So the fundamental vector space that we need to remember is a vector space that we call V. And this will just be a 2-dimensional vector space with some distinguished basis whose elements we call V plus and V minus. Now, sometimes in the literature, we'll also see these basis vectors referred to as 1 and x, because in a very natural way, we should really think of this vector space itself as an algebra. And which algebra is it? It's just this simple algebra. Okay. Okay, so this is the important vector space underlying the vector space which underlies Khovanov homology. So we have some chain complex over a field. So what's the data we need to specify? Well, we need to specify the underlying vector space and then some differential. So the underlying vector space uses very much this data of this very simple vector space, this simple 2-dimensional vector space V. And how does it use it? Well, for each vertex in the cube of resolutions, you just take a tensor product of V with itself, and the number of times is corresponding to the number of components in the resolution. So associated to this vertex, you associate the vector space V. Here you associate the vector space V to the second tensor power, etc. Okay. And the other thing that I want to point out is that, well, whenever you have a distinguished basis for a vector space, you inherit a distinguished basis, a distinguished standard basis for any tensor power of that vector space. So V tensor 2, if you now number the components, this is really the span of V plus tensor V plus, V plus tensor V minus, V minus tensor V plus, and V minus tensor V minus. Sorry. Which you can really think, which you can and should really think of as coloring the components of the resolution with either a V plus or a V minus, one of these distinguished basis vectors. Okay. All right. So now we're going to get from this underlying vector space a chain complex. So the one thing I absolutely have to tell you about today is the homological grading on that chain complex, or rather the cohomological grading on that chain complex. So this is the I grading. So the relative grading, the relative homological grading, is given by the Hamming weight. In other words, the sum of the binary digits. So this is the Hamming weight. So all of the generators here are in well, relatively speaking, all of the generators here are one more in cohomological grading than these ones. And all of the generators here are one more than these ones. So you have this flattening of the cube. But now the absolute grading, and again, I want to emphasize, I'm just telling you everything that you need to know to understand Khovanov homology of braid closures. In the case of braid closures, it's very easy. I'll just go ahead and define the zero. You fix the zero zero so I equals 0 for the complete braid-like resolution. So there's one resolution, there's a single resolution that is itself a braid, a complete braid-like resolution. And that's this one. Everything else has backtracking. And we just assert that this is level 0. So that tells us where everything else is. So of course this only works for braids. Okay. And now
Ellie?
Uh-huh.
Does it work if you say oriented resolution instead of braid resolution in general case?
Maybe. I don't know. That could very well be right.
Yes. They're the same
It
thing,
does.
right?
But for braids, yeah.
Oh, sorry. Yeah. It's fixed, so the oriented resolution is at 0 always.
Okay. Okay, great. Thank you. Okay. All right, so I've told you what the underlying vector space is, and I've graded it with respect to a cohomological grading. And now I'm going to describe the differential, the Khovanov differential. So this is a sum of maps associated to edges exiting a particular vertex. So we're defining it on this distinguished basis, and a distinguished basis element is associated to a vertex. And now you look at all of the edges exiting that vertex. In this particular case, well, here you have 2 edges exiting a vertex. Here you only have 1. But in general, you'll have quite a few. These maps are called, these are the merge M and split delta. Okay, so topologically speaking, at each vertex you have a complete resolution, and if you're just changing a single changing the resolution at a single crossing, then most of the circles will remain the same, and there will be either one circle splitting into 2 or 2 circles merging into 1. So here are some split maps, and here are some merge maps. Okay. And in terms of what they are on these distinguished basis vectors, the merge map you should think of as a multiplication map in this algebra, the natural multiplication map in this algebra. So on all the circles that are unaffected by the saddle-cobordism, you just keep the labels the same, and on the two circles that are affected, Actually, let's do it in terms of the other names for the basis. Just so you can see, it's really a multiplication. So here are all the possible markings for the circles involved. And what you're doing really is a multiplication in this algebra. And for the co-multiplication, well, you can really think of it as exchange the roles of x and 1 and reverse all your arrows. So imagine standing on your head and reversing all the arrows. Okay, so now I'm actually ready to tell you what Plamenevskaya's generator is, what Plamenevskaya's class is. So here's the definition. So this is going to be some distinguished generator in this complex of a in this Khovanov complex of a braid closure, and this is the all V minus marking on the all braid-like resolution. So it's here. And you're just, it's the V minus tensor, V minus tensor, V minus tensor, V minus guy. Okay, so the little lemma, which I've left as one of the exercises, is that this class is a cycle. Okay. So yeah, by the way, this is Plamenevskaya. And everything that I'm saying about her invariant, she proved. Okay, so this particular class is a cycle. So the key point here that will be involved in proving that is to realize that all of the edges exiting this particular vertex will have to be a split. We'll have to have a split map corresponding to it. This is an exercise. Sorry, what? Oh, merge. Yeah. Thank you. Yeah, I got it. It hurts in my head. Yes, a merge map. Thank you. Okay. And so what this then allows her to do is to define the homology class of this class. So this is an element of the Khovanov homology of the closure. And the important theorem for us of hers, I hope she'll forgive me for shortening her name for the rest of the talk, is that, so she proved more than this, but for the purposes of this talk, this is all we need. It's a conjugacy class invariant. So it's an invariant of braid isotopies in the solid torus. Closed braid isotopies in the solid torus. Okay, any questions about the definitions? Okay, so now, oh, I should have just left off the theorem because I'm about to write it again. But so what we're trying to do here is prove that that sigma is conjugate to the identity braid, which is the same thing as being equal to the identity braid, if and only if Plamenevskaya's invariant doesn't vanish, and when you compute the invariant again for the mirror, it also doesn't vanish. Okay, so now I'll have to take a detour to topology. Back to topology. And remind you that that although we typically think of braids as these tangles, these geometric objects, we can also think of them as mapping classes. So so what do I mean here? Well, if you have the end punctured disk, where the end punctures are arranged horizontally like this, so they're ordered from left to right. And let's call the set of endpoints delta. Then we can think of the braid group as orientation-preserving diffeomorphisms of the disk, which fix the boundary pointwise. Fix the set delta setwise, modulo isotopies that are fixing both the boundary and delta pointwise. Okay, so if you're not used to thinking about this, let me just tell you the bare minimum that you need to know for this talk to convince you that something like this is true. So over here we have a geometric braid. And let's, just for the sake of, because we'll need it later, let's just fix some point on the boundary. And what we're really actually going to be interested in is the action of braids on arcs that go from the boundary to the set delta. These are what I'll call admissible arcs. So say you have such an arc at the bottom. Well, you can just kind of follow it through and you'll get an arc at the top. So let's call this arc, well, we're going to call it later P0. So let's just call it P0 now. And now this is, so I read my braids from bottom to top and left to right, so my braids act on the right. Sorry, Tony. But that's the way it is in our paper, so I don't want to be overly confusing. or I'm not going to confuse myself mostly. Okay, so this is what, so if this is a braid sigma, then this is what I would call sigma acting on P0. Okay, so you can now sort of see how at least you get actions on arcs. So here's this mapping class, diff plus, that I defined over here. Diff plus minus isotopi. And if you want to know more, I highly recommend Berman-Brendel's. So if anyone could be said to have invented braids as mathematical objects, it's Joan Berman, and all of her writing is great on it. I like this. Pretty much everything I know about braids I've learned from this survey. So it goes into detail about this correspondence between these tangles and these mapping classes. But the important thing for us to know, actually, besides this picture, which is nice, is that if you look at the elementary Artin generator, so this is the positive crossing between the ith and the I plus first strand. On this side, it goes to a counterclockwise half twist in a neighborhood of an arc joining the ith and the I plus first strand. The simple arc joining the ith and the I plus first strand. So it's trivial outside of a regular neighborhood, and it just does this little do-si-do there. Okay. So now we're all set to prove this theorem. Okay, so actually really all we need to prove this theorem is a couple of pretty simple topological observations and the following key proposition. So the proposition is that if, so let's let sigma be an n-strand braid. Then if Plamenevskaya is invariant is non-zero, then sigma is so-called right veering. So this notion appeared in Andy's talk. And the notion here is a little different, but closely related. So let me tell you what I mean. So if you have this disk with the marked punctures, the marked points, and now you've also marked this point, this special point on the boundary, you can consider an arc to be admissible if it's smoothly embedded and transverse to the boundary, and connects this boundary point to some point in one of these marked points in the interior. And now we just pointed out that braids act on such arcs, and what we want is that it sends the arc to the right when pulled tight with the original. So, so for example, it could send so let me write a few words. So here's the definition. Sigma is said to be right varying. Or we'll abbreviate it RV. So if for all admissible arcs gamma, so I'll say smoothly embedded, smoothly properly embedded, no, smoothly embedded arcs with boundary equal to star, well, I'll just say from star to delta. That intersecting boundary of D union delta only at its boundary. Gamma is to the right. No, sorry, sigma gamma. Sigma applied to gamma is to the right of gamma when pulled tight. So what I mean by pulled tight is when they're made transverse to each other and there are no empty bigons. Made transverse. No empty bigons. No unnecessary empty bigons. This is actually important. So as long as a bigon has a point on it, it is not considered empty. It's not empty. Now, why am I saying unnecessary here? Well, this is actually this kind of sometimes confusing corner case, but if your braid happens to fix the isotopy class of an arc, it is said to send that arc to the right, because to make that isotopy class transverse from itself, transverse to itself in the interior, you have to just move it off of itself, and that will create an empty bigon. Okay, so keep that in mind. Okay, so now here's the proof of the theorem from the proposition. Oh, let me make a couple of remarks first. And these remarks you'll prove in the exercises. So first of all, a braid sigma is right varying, or respectively left varying, if and only if its mirror is left varying, respectively right varying. So I should also point out, and it may have been obvious to you, because we're considering all arcs, this is really a property, this right varying property is really a property of the conjugacy class of the braid. And I should also have noted I didn't define left varying, but you can see what it should mean. So when I say to the right, by the way, I should have said when viewed from sigma here at the boundary, sending it to the right. Okay, and then the second point is that a braid is both right varying and left varying, if and only if it's the identity. Or conjugacy class is the identity conjugacy class. So these will be exercises, and I give some hints about them there in these sheets, which you should pick up after. Okay. So then the proof of the theorem from the proposition and these remarks is that, so if you look at the contrapositive of this proposition, sorry, I'm getting ahead of myself. So the point is that if right, so one direction, if you're the identity braid, it's clear because you have a crossingless diagram. There are no differentials, so both of these, this is easy. So now if you happen to know that both of these invariants are non-vanishing, then it's telling you that the braid is both right and left varying by these two remarks. So So sigma is the identity. Okay, so the proposition is really the important thing to prove. And it actually follows from a really nice, it follows reasonably easily from some really nice work of other people. So here's the proof of the proposition. And this is the point of contact with this right invariant order on the braid group. So what we'll really prove is the contrapositive of this proposition, that if sigma is not right varying, then Plamenevskaya's invariant has to vanish. And the way that you do it is as follows. So the first step is to realize that if sigma is not right varying, then it's saying that it sends some arc, we don't know which one, to the left. So sigma not right varying implies sigma sends some arc to the left. But what this implies, and this will be one of your exercises too, is that some conjugate of sigma sends a particular arc to the right. This one that I was focusing on before and calling P0. So you can actually, this may appear in Tony's talk in a completely different guise, but you have these sort of interesting simple arcs, and this is the first one of them. So it sends this particular arc here that I've chosen. Let me color it so that. Sorry, I'm going to take 2 more minutes. I swear this won't take me long. To the left, to the left. So let's say, let's call this conjugate tau sigma tau inverse. Okay, but now there's this really beautiful result of Venn, Green, Rourke, Rolfson, Wiest. Ben asked me for these names after, if you like. Ben, Green, Rolfson, Rourke, Wiest, which says that this braid, so this is somehow quite natural seeming, but to me unexpected, actually has a word as a representative containing at least one appearance of sigma 1 inverse and no appearances of sigma 1. So they actually construct a word, given something that veers to the left. What they're really doing is using this collection of arcs. So this, by the way, is sort of the basis for what's called a curve diagram. You start with this collection of arcs, and now you look at how this collection is moved under a braid, and you look at it with respect to the original collection, and this gives you some information about the braid. This is where this Danois order comes up, which I definitely won't have any time to say what it is. But the point is that now it's just algebra, which I'll walk you through in the exercises. That there actually exists a particular class that you can just write down in homological grading -1. Remember that Plamenevskaya's class is in homological grading 0. Whose boundary is exactly Plamenevskaya's class. So once you have this result, you just see that it's a boundary. Okay, so I'll stop there.
We'll convene after lunch and exercises, so you should pick up your exercise.
Yeah, actually, so I should note, my exercises and Tony's exercises are here. I couldn't figure out how to get the thing to staple, but just make sure you pick up 2 different sheets of paper, and you'll be fine.